Okay. Well, thanks everybody for coming back. So we're in the simulations of common envelope evolution session, what is for me late morning. Hope it's not too early or late for you. We have 4 talks on a few different topics, and of course, global simulations are covered in not just this session, but in a number of sessions. And so I thought instead of giving an introductory talk, what I do is that pose some questions to think about and highlight a few of the speakers both before the session and after, some working on things other than global simulations that who have addressed these questions or have had interesting things to say. One of these questions is, so we have this picture of common envelope evolution as proceeding in a few different distinct stages. The evolution of the binary system up to the onset of dynamical instability, the onset of dynamical instability and the dynamical spiral in, and then a termination at a finite radius or finite separation or merger, and that final stage typically involves a slow spiral in, self-regulated. And so the question is, how is this picture modified when the thermal or for that matter nuclear timescales compete with the dynamical timescale? So we'll have a couple of talks involving global simulations of stars for which this can happen, at least in their outer envelopes. This is AGB stars and red supergiants in particular. And we'll also have some interesting talks on white dwarf and neutron star core mergers and explosions within common envelopes. And of course, in these sorts of circumstances, we can't get away with assuming the envelope to be adiabatic. And in the cases where we actually have explosions, of course, then we have to include nuclear reactions as well. So when the thermal timescale is comparable to the dynamical timescale, we need to consider energy transport by means other than simple advection of material. So radiation, convection. Emily Wilson gave a very nice talk this morning, earlier, I should say, on convective energy transport, and of course I mentioned nuclear reactions. And one thing that goes with radiation, actually, with these stars, since they're very extended and often have very cool envelopes, is the potential importance of dust chemistry, changing the opacity and allowing for radiation pressure to play a role in removing material. And so there'll be a talk on Friday, I believe, on this, not in simulations, I think, but in observations. And of course, observationally, dust plays a role in obscuring our view of what's going on, especially in massive stars. So another question, is tidal circularization a prerequisite for a binary system to survive the common envelope phase? And more broadly, how does tidal circularization affect the initial conditions for the dynamical end spiral? For a long time, global common envelope simulations have been initialized by kind of simple means, by placing the secondary on, I guess the companion, let's say, on the surface of the donor. But more recently, we've seen simulations where initial conditions have at least tried to relax into a binary system, but there's more to it than that. There's the leading up to the loss of dynamical stability, and that can involve significant mass loss, as well as we saw in Morgan's talk, tidal changes to the donor's structure. So that's something important to keep in mind in setting up these simulations and making a smooth transition from the phase that we can't afford to simulate in 3D to the phase that we can. We'll also see some talks today and on, I believe that was on Friday as well, on eccentric initial orbits and the effect that those have both on the common envelope, development of common envelope, and the final outcome, the eccentricity of the final outcome. So one general lesson I take from especially Morgan and Andre's work is we need to carefully consider both the setup for these for these common envelope simulations and the approach to loss of dynamical instability. And so we'll have some talk. We'll have a talk by Bruce at the very end on winds, and we'll have a talk by Andre Pecha on semi-stable mass transfer. And then finally, how exactly is energy transferred to the envelope? When we include only a subset of the actual physics that is in the problem, we of course limit the means by which we can actually deliver energy to the envelope. Not simply it's not simply a matter of having the right amount available, the reservoir of energy, but having the physics in the simulation that allows that energy to be coupled to the envelope. And many simulations have shown sort of a gravitational slingshot type effect, dynamical friction from the wake that the companion produces. There's some shock heating, doesn't appear to be a great deal, but again, all these effects contribute. There are a number that are more difficult to include in or impossible to include in a global adiabatic common envelope simulation. In particular, for example, excitation of waves or instabilities that typically requires very high resolution and control of dissipation in the numerical method. Of course, we'll have a whole session on jets, accretion in jets, and that again is at least doing the accretion and jet launching self-consistently is a resolution challenge as well. And we've seen a couple of talks already on magnetic fields and their effect, apparently not having a big effect on the in-spiral, but producing jet-like structures that may contribute to the shape of the outflow. So in general, it's often easy to measure forces in a simulation. It's often difficult to actually extract these energy transport or energy transfer mechanisms. Some of them are non-local, and of course with convection or with excitation of very fine scale instabilities, shear instabilities in the wake of the secondary, for example, the companion, the resolution effects can be extreme. So these are a few questions to think about while we listen to the simulation talks in this session, and so we'll start. I'll stop sharing here. Let me enable our first speaker to share his screen, and I will monitor the. Oh, let's see. Did everybody else? Oh shoot, was okay. So I've just realized in the chat that some people weren't able to see the screen. Is that okay? I see a bunch of yeses. Black box over the slide. Okay, so I think that was another window. Sorry, this is running Zoom under Linux. So Miguel, I'll give you a 2-minute warning, and why don't you go ahead?
Thank you. So hi, my name is Miguel. I'm going to talk about common envelope evolutions, but doing simulations on thermally pulsating HGP stars as donors. I'm working with my supervisor, also Marco, and with our collaborators at Monash, which is Mike Lau, Daniel Price, Rio Saki Hirai, and Ilya Mandel. So typically, common envelope simulations have used RGB giants or early giants as donors. However, more recently, have been published papers by San and Shamandi using HGP giants. And we even try to push a little bit further the boundaries here using a thermally pulsating HGP star with a point mass companion, so that the mass ratio is 0.38. Okay, so for this one, we use the MESA code, and we evolve start from the 0H main sequence with 2 solar masses up until the thermally pulsating asymptotic giant branch. So just a little bit of background about this. The asymptotic giant branch is characterized by sudden expansions of the surface of the radial expansions as a product of the helium flashes that happens in the inner layers. These radial expansions typically last a few centuries. So it's really interesting because for this mass regimen, we have that is the first time that the star reaches to certain considerably larger values compared as the RGB phase. And this is relevant for us because that means that we can create scenarios where the star is about to fill the Roche lobe, and even a little bit more than that because of the expansion. So we choose a particular stellar model in which the star is reaching 260 solar radii, and you can see here in the plot in the red star that I'm putting there, and it will continue expanding during around 200 years and then continue contracting. However, the actual size will be larger than 260 solar radii for about 400 years. And that's represent a unique opportunity to see how the binary can be triggering a mass transfer and therefore a spiral in the common envelope. For this, we use the phantom code, which is SPH algorithm, and we apply 3 equation of states for 3 different models of stellar profiles. One with ideal gas, adiabatic, one with ideal plus radiation pressure, and the third one using the tabulated MESA equation of state. Here I'm showing you just the standard things for the relaxation that everyone uses, which is basically just replacing the center of the stellar profile with a point mass particle. In this case, we use 0.65 solar masses because this represents around the value of the carbon core. Also because we have to play a little bit with this parameter to properly stabilize the model. And even further, we use the new stabilization procedure by Lau. He will publish this year, hopefully. Anyway, so after that, we just run the models, the 4 different models from the Roche law overflow. It's important to note that for the ideal gas, for the pure ideal gas, we use 2 different resolutions that you can see here as blue and orange, the high, low, and high. Green represents the radiation pressure, and the red one is the mesoquation state. And here you can see that obviously the ones that have a larger time scales for the full evolution are the ideal gas, as expected, since they are the most stable and they don't contribute too much for the thermal energy. They also tend to have a shift between them of around 2 years, which is important because everyone knows that the mass transfer is dependent on the resolution. However, we see that even with increasing, in this case, 10 times the resolution, which is it was 100,000 particles, and the high resolution is 1.3 million particles. We observe that the shift of the time scale is around 2 years. And the whole simulation, even with the larger time scale, it's 1 order of magnitude less than the previously mentioned thermally pulsating time scale. So this means that according to our simulations, the common envelope can occur in this thermal pulse, and this applies for all models. The final separation for all the models is between 20 and 30, and it's pretty similar to using a common envelope evolution with an RGB star, which was really used by Ricard in 2019. However, the ideal gas equation state has a slightly larger separation. Now, here I'm showing you the values that we define of the render density for the start of the spiral and the end of the spiral. using the Sand and Ivanova criteria about calculating the separation times the period over the A dot, and checking when the value is smaller than 0.1. So applying this for our orbital evolution, we found that the values are in the same order: ideal low, ideal high, radiation pressure, and mesa, and the times are shown in the renders. We can see that the first three models are pretty much consistent, even though the times, the absolute times are varied. The events or the key moments, they're typically the same morphological speaking. We also notice there's a small ring that appears in roughly the first three simulations, particularly in the ideal high resolution, and this will be important later. So in this ring, it has a certain bound mass, which will be relevant in the next one. But however, here we can see that the bound mass of the first three models are roughly the same, albeit the time scale is slightly different, but that was expected. We also see that there's a first unbounding, and then a second slightly less and a little bit slower unbound mass. We also see that the mesa equation of state model tends to typically unbound the whole envelope almost entirely. And we also see that the radiation pressure for this mass regime is basically insignificant. Okay, so here I'm going to show you the basically the high resolution ideal gas, which is our baseline model, and we can see here that the mass transfer begins immediately, since we know that it starts expanding. And we also notice that the first 4 or 5 years is typically stable mass transfer and not that much, even though it doesn't look, it's not that much secretion. However, around 12 years, we start to see the spiral phase a little bit more deep. Up until 15 years, we have the plunge in phase, in which basically this ring that I probably mentioned is formed. This is relevant because this ring comprises around 50% of the unbound mass of the first three models. And it's relevant because we also notice that after that, there's this plateau on the bound mass that lasts a little bit more until we have the second part of the unbounding. This ring that is formed it's most likely dissipated in the first years, so it will probably not be part of any post common envelope morphology. And here I'm going to show you just in terms of the energy budget, where is the energy coming from, if it's internal or kinetic. So the first row is basically just showing the total energy, which in this case we're defining it as the kinetic plus potential plus internal. The blue is basically unbound in the first row. And the red is, the blue is unbound and the red one is bound. The second row is basically the same thing, but just ignoring the kinetic one. And we can see the ring in this part. And the third one basically tells us, is basically the logarithm of the ratio between the kinetic and the internal, which basically tells that the blue in the third row is if it's dominated by kinetic or if it's dominated by internal energies, which is important because this tells that for the ideal gas, all the unbounding is kinetically dominated. All right, so for the results, we had the main result is that the common envelope takes place in around 20 years compared to 400 years of the pulse period. So this means that at least in the simulations, it's plausible to have the common envelope evolution happen inside the thermal pulse. The second one is that the unbound mass fraction is really different between the first three models and the mesa equation state, which is 15, 17 for the first two models roughly, and 99% for the mesa equation state. Radiation pressure, as I said before, it makes little difference on the simulation overall for our intents purposes. And the full result that we can conclude here is that the ring that appears has roughly 50% of the mass, which of the unbound mass, which is roughly 0.5% of the total envelope. And this ring doesn't appear on the Mesa equation state, which is basically just radial, has a radial expansion of the whole envelope. For the future work, we want to test this same model with other types of companions with different masses, which basically means changing the mass ratio. We also want to consider lower the binding energy. So that means probably just using a different model, which probably like a higher pulse in which you have a slightly larger expansion, which means having a lower binding energy. And hopefully we can continue to simulate the post-common envelope structure as it was done by Sue in 2020. Yeah, so that's basically it. Thank you, everyone.
Thank you. Actually, didn't have to give you the 2-minute warning, but so we have lots of time for questions. Please go ahead and ask in Slack, or anybody who wants to can just unmute. Okay, well, I have a question. So do you have any sense of why the ring shows up in the ideal gas case and not in the Mesa case?
Well, it's because it's a partial explanation, since we are in the process of finish the analysis of all the simulations, but it's a lot to do with the recombination energy, because the Mesa equation state, typically we just apply the thermal, there's this confusion with thermal and internal, but basically the recombination energy is being applied in as a whole for the gas, and this means that you have a little bit like higher puff. I don't know if this like this puffer or a little bit more expanded envelope.
So it's still there, it's just lower density.
I'm not sure. It doesn't appear to be at all. It's just a radial expansion. It looks basically just spherical, well, not accretion, but expansion. And also because of the time scale, if you check the time scale, you start unbounding material way before the spiral happens. Okay. And I think it has to do with the dynamical. The other factor is that you don't have enough time to contribute with the orbital energy, because for the first 3 models you have the orbital energy basically doing most of the job, but the current or Mesa model is a little bit less stable for the final model for the Mesa equation state profile. And that tends to that means that you have a little bit rougher mass transfer, and since it's a little bit more faster, and this doesn't allow for the companion to make the transfer energy of the orbital. So I think that has to do, but I'm not completely sure, since we haven't finished with the analysis of the energy budget and the recombination energy and the factor, and what is the factor that it plays in this situation.
Okay, thanks. So we have a couple of questions. Tomek asks, what is the expansion velocity of the unbound material?
That's okay. So the expansion is typically, I don't have that number in the back, but if you check the render and the velocities, it's in the inside, it tends to be around 20 kilometers per second, but even further away, it tends to be a little bit slower, around 30 kilometers per second.
Okay. And just it's out of order, but linked to the first question. Carmen Sanchez asks, what about the rotation velocity? I'm not sure which rotation speed we're talking about, but
yeah, I think I have to say that that question is tricky in this case. I wouldn't be able to say if there's. I mean, you mean the velocity of the unbound material? Because
that's I don't know.
There's it's not well, I can say it's negligibly comparing to the radial velocity. But I couldn't give you an exact number for that.
Okay.
But it's definitely negligible compared to the radial velocity.
Okay. Roger Hatfield has a couple of questions. How well did your 3D models' energy profiles match their initial 1D model?
In terms of energy, it's difficult because, as you know, the mapping tends to, especially with from grid to SPH, tends to be quite tricky. We tend to, I can give you the comparison with the velocity escape of the particles, which tends to be quite low for the first three models, tend to be around less than 0.3 the escape velocity overall. However, in the mass equational state, we have over 0.4 times the escape velocity for less than 0.01% of the particles.
Okay. And how did you control time step choices for interactions with the point mass accretor?
Well, that tends to be with the current time of the code itself. I don't control that. I mean, I could change the current factor, but I typically just use the default value.
Okay, so we've got a comment from Alexei. The mass transfer phase preceding the common envelope evolution is called onset of mass transfer. Stable mass transfer by definition proceeds on timescales longer than dynamical and does not lead to a common envelope. That's right. Yeah. So it's a loss of stability that leads to CE.
Hey Paul, I don't know if you noticed, but there are 4 raised hands in the Zoom participants window.
Oh, thank you. I'm looking at the Slack channel, and okay, I'll bring up the participant window. Sorry about that. Hila, I see.
Hey, thank you. So I have a few questions. Perhaps I did not understand well, but so the first one is, how did you calculate the radiation pressure? And then, so you initialize, I guess, the simulation when it's on the minima of the pulse, right? And then you showed yeah, okay. You can answer that.
Yeah, sorry. It's okay. So the first one is you first calculate the temperature based on the ideal gas, which is really simple, and then you apply the equation for the radiation pressure, and you use in this case the code use a Newton-Raphson method to calculate the new value for the temperature that matches the internal energy, which is the total of the radiation plus the previously calculated internal energy using just the ideal gas. So that will give you a new temperature, and that will basically redefine the second term, which is the radiation pressure.
I see. Okay. And then regarding the in-spiral snapshot that you showed, so did you use like the criterion at the point of the end of the spiral? Because are you sure that it is the end of the spiral? Because it looked for the first 3 simulations that it's actually still ejecting mass with this ring.
Yes. So the issue here is that it's really complicated. If you let me go back to the actually, well, this one can be quite. This is for question, but I probably will be useful to use this one. Okay, so if you notice it, right after the steepest point in the ideal and radiations models, you have this eccentricity, right? So the problem with this eccentricity is that it tends to get in the way with calculating this value that we use for the criteria, which is basically A times P, which is the period, over A dot. because it tends to be quite noisy, right? So for this one, you have to smooth things. There's no other way. Trust me, I try, and the only way is that it just smooth the values. And when you do that, it's you tend to have and the problem is that how do you smooth it, right? There's other several ways. You can use a spline. In my case, I use a SAGOP filter to do it, and I use certain criteria that I'm going to publish in my paper, which is basically the just taking the filter has two parameters. One parameter is the polynomial order, which I use as 1 because using more than that will be overfitting, and it will give an offset of the signal. The second one is the window length, which is basically how many data points you use for the parameterization of the polynomial for certain set of values. And this one, I use it in a way that the highest difference between the original value and the smoothed value should not be larger than the size of the sum of the sizes of the softening lengths of the point mass particles. It looks quite messy, like saying all that, but the issue is that there's not a perfect way to calculate it, the spiral here. I mean, you can see it. You can see, okay, around of this point or certain point, you can say that it's ending, but it's really difficult to say how to apply certain criteria. That's why for even this criteria, Sand uses, I believe, 0.1, and Ivanova I believe, use 0.01, and that's for my simulations. Gives you a range in the spiral time scale considerably different between one another. So there's not like a perfect recipe to calculate the spiral time scale. In my case, I'm using this one, and it was the one that seems to fit a little, that seems to do the work in my situation. However, this may change eventually during the remaining analysis of the simulations.
Okay, so I think I apologize to the people who raise their hands. We're going to have to move on, but if you could type your questions in the Slack channel, Miguel will be able to answer them. And I see Luke's question as well. So let's go on to the next talk. Thanks for your talk. And
sure.
Let's see, Mike.
Hello. Let me just share my screen.
Mm-hmm. And I'll give you a 2-minute warning.
All right, thank you. All right, so hello, I'm Mike. I'm a PhD student at Monash University, and I'll be talking about my attempts to produce 3D hydro simulations of a massive star common envelope. And my collaborators are Rio Hirai, Ilya Mandel, Daniel Price from Monash. And at Macquarie University, I'm also working with Ursula and Miguel, whom we've just heard from. And apologies, because it's a short talk, I'll probably not be able to go over important details that I really like to discuss, but hopefully you can perhaps mention them in the Q&A section. So to begin with, I'll provide a bit of background. Because of the complexity of this common envelope phase, a key method of studying this evolution has been to rely on hydro simulations, detailed simulations of common envelope. And some of these attempts over the past few decades are shown in these pictures on the left. And the key questions that these simulations address are, can we fully eject the envelope in these simulations? And if we do, what is the post-common envelope separation or the final separation of these systems? And these simulations typically are limited to modeling the dynamical plunge-in phase of the common envelope, although there are attempts, for example, there are starting to be more and more attempts to start the companion at a larger distance, for example, where the donor would fill its Roche lobe. And these simulations have also been mostly unsuccessful in unbinding the entire envelope self-consistently, without making, for example, some assumptions about how recombination energy is deposited and whether it's fully thermalized locally. And moreover, these simulations have really mainly focused on low mass donors, roughly about 1 to 2 solar masses. But there have also been some recent works to explore high mass donors from Paul and collaborators, and also a recent submitted paper from Jamie Law-Smith and collaborators. So, however, we really ought to understand massive stellar donors in common envelopes for a number of reasons. First of all, these lead to forming different class of systems, for example, like gravitational wave sources and high mass X-ray binaries, and etc. And however, massive star common envelopes are qualitatively different from their low mass counterparts, and they are often problematic to simulate for several reasons. First of all, as mentioned by Paul and others, the thermal timescale in the envelope can be comparable with the dynamical timescale, which means that an adiabatic simulation may not be sufficient. That's, for example, explored in Paul's 2019 IU proceedings. And also, there's significant pressure support from radiation in the envelope. And in my work, I'm focusing on addressing this second point. So take as an example, a 12 solar mass red supergiant. Here I'm plotting on the vertical axis the binding energy integrated from the surface as a function of radius on the horizontal axis. So the quantity I'm plotting is this integral here, where this second term gives rise to the gravitational potential energy. And the first term, I include an internal energy contribution to allow for the possibility of internal energy to be used in ejecting the envelope. And I'm plotting these different lines here with different contributions to the internal energy. So the black line here is just includes the gravitational potential energy, but the colored lines calculate the internal energy assuming different equations of state. So if I just assume an ideal gas, I have this red line here. So the interpretation is the addition of this gas thermal energy could make the energy less bound if it's fully used. And in the blue line, I use a gas plus radiation equation of state. So the idea is that the inclusion of radiation effectively lowers the adiabatic index of your envelope, which leads to a higher internal energy. And moreover, if I use a equation of state that also includes recombination, my envelope becomes even more unbound. So in this case here, with my choice of what the core is, we get something like an 80% lower binding energy. So again, the message from sort of this plot is that we could anticipate that different components of internal energy may help unbind the envelope. And particularly in massive stars, there's the addition of radiation pressure, which is not important in low mass stars, but more important in massive star envelopes. So how do we quantify the effects of radiation and recombination, perhaps, in massive stars? Our approach is to perform a series of simulations with different equations of state. And we're using the same donor star with the same hydrostatic structure, same density, same pressure, but different internal energy profiles and temperature profiles as prescribed by the equation of state that we assume. So again, the different equations of state we're using are just an ideal gas equation of state, and then a gas plus radiation equation of state that assumes where we don't do full radiation transport and we just assume local thermodynamic equilibrium. And finally, a full equation of state where we include also ionization and recombination. So for this, we're just using something like the Opal, the equation of state tables as provided in MESA. So the idea is that by comparing simulations made with the first and second equations of state, that would reveal the difference between a low mass and a massive star common envelope, namely the addition of radiation. And by comparing the second and third equations of state, that would reveal the role of recombination in a massive star. And for our simulations, we're using the phantom code, which is a smooth particle hydrodynamics code. It has also been used for previous common envelope simulations with low mass stars, and also for Miguel's simulation, as he has just discussed. And the figure on the right shows the setup of our simulations. At highest resolution, we're using 2 million SPH particles. The sphere on the left is our donor star. We're using a 12 solar mass red supergiant donor in orbit with a companion, and we're using 2 different sets of simulations. One with a 3 solar mass companion, which could correspond to a main sequence star. Another set with about a 1.26 solar mass companion, which could correspond to, for example, a neutron star. And for this red supergiant donor, we're actually using an artificial profile where we set the entropy of the envelope to be flat. That's because our simulations are fully adiabatic, and we lack we're not modeling energy transport and any sinks and sources in energy in order to sustain convection in the envelope. And so we opt to, as a first attempt, to suppress this convection in the envelope by just having a flat entropy. So here I show some of our simulation results. This will be a movie of our medium resolution simulation. This is the donor star, and towards the right, in a very small dot, there's the companion. And so we begin with the donor star filling its Roche lobe from the onset of Roche lobe overflow, and we see gas settling in the disk around the companion here. Then I pause this simulation at around where the companion will start its plunge in as it enters the envelope. Notice here about 30 years have elapsed, and most of the simulation time has really gone into this modeling this onset of Roche lobe overflow. And with the remaining evolution, the dynamical in spiral being a rather comparatively short phase. So I'll play the rest of the movie now. There we have it. Now I'll show a movie from our high resolution simulations, but now showing a density cross section. So we're looking face on onto the orbital plane. So this is for the gas plus radiation equation of state. And at high resolutions, we start with the donor and companion slightly closer to each other, such that the donor overfills its Roche lobe by 30% due to computational resource constraints. So I'll play the movie now. And this is what we get. And by the way, I've forgotten to mention that we're modeling the stellar core and the companion with these softened gravity point masses. And we don't allow them to accrete. So these are sort of the qualitative results from my simulations. And now I go into addressing the key goals of these detailed simulations, namely what are the final separations and amounts of unbinding that we observe.
2 minutes.
So to look at the final separation, I'm plotting the separation versus time, the separation between the donor core and the companion for different equations of states, as shown by the different colored curves. So what we see here is that if we compare the results for the 3 different equations of state, that in the same direction where we decrease our binding energy from left to right here, because we're increasing the internal energy content in the envelope, we also observe, as expected, an increase in the final separation in the same order. So the fact that the blue curves is above the red and the green above the blue. So this is expected from sort of a energy formalism, where because there's more energy available in the envelope, you don't have to inspire as much to start unbinding, to start stalling in the envelope. And the next thing I've looked at is the amount of unbound mass. So these 3 panels plot the fraction of unbound envelope mass. So we're unbinding everything as we go to 1 as a function of time, and also include the different results for different simulations here, because we're able to run the lower resolution simulations for longer, and we actually observe more. And because towards the end of our simulations, the amount of unbinding is still increasing. We're able to see more of the unbinding as we run the simulations for longer. So again, what we see again is that as we use an equation of state that effectively decreases the binding energy of the envelope, not only do we increase the final separation, we also typically increase the amount of unbinding. So we get like few tens of percentage of the envelope mass unbound for the ideal gas and gas plus radiation cases. And we almost unbind everything when we look at the full equation of state, at least for the medium and low resolutions.
Okay, if you could wrap up.
Yeah, thank you. I'll quickly wrap up by displaying this slide. So we've produced 3D global hydro simulations of a common envelope involving a red supergiant, and we've compared results assuming 3 different equations of state. We find that unbinding fractions of few tens of percent, possibly ejecting everything when we include recombination. And the final separation also depends on the equation of state, increasing with the internal energy reservoir. And that is all. Thank you, and I'll take any questions.
Thank you, Mike. That was a great talk. Yes, any questions? Okay, so I see some applause. Fritz.
Yes, maybe I've missed it. How do you measure the unbound mass fraction there? What was your criteria?
Yeah. Sorry, I haven't made that clear, I guess. So here I'm plotting, I'm using the total energy greater than 0, where total energy combines kinetic potential and thermal energy. I don't include recombination energy in the criterion. But I've also made these plots where I just include the kinetic and potential energies, and they are more or less exactly the same towards the end of the simulation. So because I guess most of the gas has cooled and the thermal energy is really gets converted into kinetic energy.
Okay, do we have any more questions? Yes, Noam.
Yes, so can you see my writing? What is the mass of your envelope? Your mass of the envelope?
So the mass of the envelope that we define here is about 8 solar masses.
Yes, this is what I thought. So 8 solar mass, if you take this mass and multiply it by the energy per recombination, recombination is about 50 kilometers per second. So this is the energy that recombination will give you, okay? So if I do the calculation, then 10 to the 34, and from here I get 25 times 10 to the 12. So I get 2 times 5, 10 to the 47. This is the energy that you get from a combination. Now let's look at the luminosity of the star. The luminosity of the star, what is the luminosity of the star?
Sorry, I don't recall that off the top of my head.
Okay, the luminosity of the star is say 10 to the 5, massive star, and the simulation is 10 years, 3 times 10 to the 8. So during this 10 years of simulation, the convection, this is Wilson talk, will carry an energy that I see here. This is 10 plus 14, 10 to the 47. So your recombination energy is about the luminosity of the star. So my point is, if you do this simulation and just put the luminosity of the star and let it run for 10 years, the star will unbind itself. This is my point. So including recombination energy without including convection, I would say bluntly, it's wrong. This is my point.
Yeah, I completely agree that convection is very important, the energy transport by convection, especially in massive stars. But the main idea in this study is to perform a series of controlled experiments where we look at different equations of state and the effects of the different amounts of internal energy, and not exactly on trying to model reality here, where convection will be important, radiation transport will be important. So that's sort of the next step.
Simulation is in place, I don't say, but I think in the discussion, you should do this calculation. I just did an order of magnitude, but the point is you have more in the combination than in the luminosity, but the convection can carry much more, because if I add luminosity, the convection will be more efficient, okay, by the velocity and whatever. So the convection is very efficient in carry energy. So using all the recombination energy is very dangerous. So I just for my estimate here, but we wrote about it several papers, and we claim you cannot do with the recombination. Now, what do I do with the recombination? This will be tomorrow session by Tomek, that we will talk about the transient objects. I think recombination energy actually make us see this object by ejecting material, and you have recombination if convection transport it out, and then radiation will see luminosity. This is what happened in supernovae. In supernovae, most of the recombination goes to core collapse supernovae. So this is my point. This is it.
I think as
thanks for the input, Noam.
Fritz mentioned this morning, it's really getting an upper or lower limit based on, when we include all of it like this. Steve.
I'm just wondering what the effect of including a turbulent pressure gradient would be. Since you're generating turbulence, this is also going to be connected with the convection, especially if you're generating additional convection in the models. Not in these, but just in a general case. I mean, this has been used in ejection models for winds and envelopes, for example, the Yager. I think it's built into MESA.
Yeah, this is not something I've looked into, unfortunately.
Well, it's just you're at the margin already. So if you increase the temperature gradient, you're going to have a nice acceleration mechanism. Sorry, if you increase the pressure gradient. So during the in spiral, if this were to generate a turbulent field, you would have an additional term besides the kinetic energy, because this isn't a mean value. It's going to go like the square of the turbulent velocity. So
in general, the spiraling in, it's not only deposit thermal energy, it also excite waves. We had a talk today.
That's my point.
Yeah,
that's my point now.
Exactly, yes. We had talks and people mention excitation, but it's not only like tidal, that the orbital period is longer than the fundamental pulsation. When the star is inside, it excites a short period waves which can deposit energy, and indeed these waves can be important, I think, even to planets that enter the envelope.
Yeah, but the buggers are also going to be nonlinear, so they're going to cascade. It isn't just that you're depositing energy, you're also creating the equivalent of a pressure gradient. That was my only point. No, nice results.
Thank you for raising this point. It's not really something we have considered yet, but.
Let's see, Fabian.
Thank you very much. Mike, beautiful work. I have a question that is maybe not actually addressed so much to you, but sort of towards the discussion that Noam started on convection and things. And I have always one sort of conceptual hurdle in my head, more or less, in my thinking of convection and whether it is going to be able to transport energy. And that is, if you have a massive companion that spirals into the envelope, then it perturbs the flow and the entire structure. And what I've never really grasped yet is how much could convection then still sort of carry in such a perturbed envelope. I can easily see this argument work out, for example, if you have a low mass companion that gets dragged into the envelope and then it just sort of spirals through the envelope without perturbing it much. But once you start sort of ejecting part of the envelope and you're lifting off the envelope, and then I'm really wondering, can you have sort of the standard vanilla-like convection? And maybe this is more something for a discussion that we can have later, but I just wanted to raise this comment as we have this point again here.
Yes, the density is going lower, so the convection will be less efficient. So I don't say you cannot use at all the combination energy. Some of it you can use, and you are right. If the envelope is expanding, density will be lower, so convection less efficient. Of course, all this can be done together, and this simulation is very nice in giving the upper limit of injection, but I think eventually one should include convection, and the simulation here are very beautiful and in place. Just in the discussion, one should note the limits and so on that we discuss here. But these are very important and nice simulations, I agree. And convection will be lower in inflated envelope. This is also clear.
Mike, do you want to respond to Fabian's comment?
Yeah, so yeah, I agree with Fabian's comments and also Noam's response to it, that this is just an upper limit, and to include more in the discussion, more about the possibility of this convection lowering the actual unbound envelope mass in the actual astrophysical transient instead of in the numerical simulation.
Fritz, did you put your hand up again, or is it just?
Yeah. Actually, I wanted to make a very similar comment to what Fabian actually said before. So from looking at the 3D simulations, I also have strong doubts that the picture of convection, as you have from this kind of stellar structure model, really holds here, and that this really applies. I think you can have two regimes. So one regime is you either have a when you have a very light companion, that it does not distort the structure of the envelope very much. And then, of course, it's possible that convection still carries away the energy that's released from the orbital energy, and it works that way. But once you actually really start to distort the envelope, and this is actually the prerequisite for releasing recombination energy, then I think you completely destroy the convective flow field. And the entire envelope is threaded by the spiral shock that actually develops. And you don't have a spherical structure anymore. And I don't think that you actually have convection that actually goes through the entire envelope anymore and transports energy to the surface in this case.
I think that's a really good point. The picture we have in our heads of how convection works is really based on, mixing link theory, or some combination of that with Kolmogorov turbulence and an incompressible steady flow, and that is not the situation here.
Maybe is it fair to say, though, that we're still talking about effective transport of energy to lower optical depths where it can then radiate away? And yes, it's not subsonic convection because there isn't sort of a time scale for that, but it is sort of sonic movement of gas to lower optical depths.
I think it's useful to distinguish between what you'd call advection, sort of as a laminar motion, and more disordered energy transport.
Well,
Interestingly.
So I think what you have is really the advection of material sort of that's flung out by these spiral shocks. And that is actually what you follow in the hydro simulation. That's resolved in the hydro simulations. The only thing that is missing is that you need to include radiative transfer to know where the photosphere is and whether you lose a lot of recombination energy over that. But I don't think that convection actually is the way to transport it there. It's actually the very dynamical sort of flinging out material if you have a strong interaction with a massive companion. It's different if you have a light companion, then the structure is not so much distorted. But I think in Mike's simulation, he's in the regime where convection really is completely, it's dominated, the flow is dominated by the interaction of the companions. So, convection is not the leading transport mechanism anymore.
Steve, you have another question?
I was also just wondering if you're including composition gradients in the massive star.
So currently in my simulations, we assume a uniform composition, but that's really just because in the part of the star where we model the envelope, we're taking as the envelope the convective envelope, where the gradient is what the composition is uniform in there. So we don't include any composition gradients.
Okay, so you don't have any additional buoyancy effects other than thermal.
Yes.
Okay.
Okay, thank you. Thanks, Mike, and thanks for all the good questions. I think we should move on. Hila, If you could, yeah, thanks.
Yeah, thank you.
Go ahead and share your screen.
Yeah. Okay. Can you see my screen?
Just about. Okay. Yes, I can now. Yep.
Yeah. Great.
All right. Give you 2 minutes warning.
So hi everyone, and thanks to the organizer for this conference. I'm Hila Glanz, a PhD student at the Technion in Israel, under the supervision of Professor Hagai Peretz. And today I'll present our recent work on the common envelope phase of eccentric binary system. So most of the studies on the common envelope evolution assume circular orbit at the onset of the common envelope, since the orbit can be circularized by tidal interactions before the common envelope begins. But as we heard today by Morgan McLeod, Roche-Lobe overflow of eccentric binaries is not necessarily a spatial scenario. And in addition to maintaining the eccentricity while ejecting mass during the Roche-Lobe overflow, initial eccentricity can be achieved by dynamical interactions of the system with other components, via Lidov-Kozai scattering, and even following a triple common envelope scenario that caused a merger of the inner binary and ended up with a short period binary that later on experienced another common envelope episode after one of its component fields its new Roche-Lobe. Now we ask what happens to this eccentricity during the common envelope spiral in. So as we heard today, post-hydrodynamical studies that calculated the eccentricity at the end of their simulation find that even an initially circular orbit develops eccentricity by the end. Because on the one hand, we have the tidal dissipation that decreases the eccentricity, but the mass ejection and other processes through the dynamical friction increases it. So the question is, how strong is the tidal circularization during the spiral in, and how it connected to the mass loss and the ejection processes? So by the end of this spiral in, the entire envelope might be ejected away, but recent studies show that it might be ejected in a longer time, and therefore some, if not most of the envelope might still be bounded at this point. The eccentricity can therefore still change, either by interactions with bounded gas and fallbacks, or by tides, but in a longer time scale than the dynamical spiral in time. And one can maybe follow this evolution if existing observations. Observationally, post-common envelope systems are assumed to have one component, which is SDB star or white dwarf, which is the remnant of the giant core. But most of the observational data of such systems lack the information about the eccentricity, or sometimes even assume it to be zero. But in systems that we have this information, we find the vast majority of them with small but non-zero eccentricities, with a few systems with large eccentricities. And we therefore expect that the eccentricity at the end of the spiraling to be relatively low, but still related to the properties of the system. And in particular, we want to understand its connection to the mass loss. So understanding the role and the evolution of this orbit and eccentricity along the common envelope maybe shed more light on the type of processes that are involved in the common envelope ejection and their timescales, as well as help us understand the evolutionary stage of the post-common envelope system that we observe. Now I'll briefly present our simulation method. So we ran everything via the MUSE framework. We use MESA to simulate the stellar evolution of our primary star into a giant with a desired radius and type. And then we mapped this model to a 3D SPH model with 250,000 particles and the core and companion as point masses. And we use Gadget 2 as our SPH code. And after a few dynamical times of relaxation stage, we placed the companion in most of our simulations at the orbit's epicenter. And we ran the simulation of the common envelope evolution for a few dynamical time until the orbit stabilizes or the separation between the two cores was lower than what should lead to a merger. And overall, we simulated 26 different systems, and I will now show some of the results. So we began by simulating a different configuration of this known system of one solar mass red giant with 0.6 solar mass companion, with 0 eccentricity ends with a short period binary with some eccentricity at the end, as can be seen here. And we simulated it with 6 different initial eccentricities, all have the same initial pericenter, just on the envelope's edge, but different epicenters due to the different eccentricity. So first, we can see this initial amplification of the eccentricity for the first 2 simulations. First, the eccentricity increases, then the orbit rapidly circularizes, and we can see that the eccentricity decreased significantly for all the simulation during the spiral, but is still presented. And for the higher initial eccentricity, the final eccentricity was also higher. And we also find that the muscles is much larger for the larger eccentricity. And the final separation here was also larger, as can we see here in the zoom part on the final stage of each simulation. So now let's focus on the simulation that began with eccentricity of 0.95, this blue one. So here we see the separation between the 2 cores and the unbounded mass for the same simulation. And this graph shows very well that most of the mass ejection happens during pericenter passages. And we can see this going up like a stair for each pericenter. And we can also see this last near stair of the unbounded mass, which is when the orbit stabilizes, as we also saw for the eccentricity. So now let's see how this evolution looks like. So we have one solar mass red giant with 0.6 solar mass companion grazing its envelope at pericenter with an initial orbital eccentricity of 0.95. And to save time and reduce numerical errors, we begin this simulation when the separation is more than twice the Rochlov size, so that the giant and companion do not interact earlier in the orbit from the epicenter, so here in this point. And we see both views of plane parallel and perpendicular. So here the orbit is toward us. So now we have the first pericenter and enormous mass ejection. And now is the second epicenter, which is slower, and we can see that the companion took mass with it without throwing it away. And then we have another pericenter, an episodic mass ejection. And now the fast spiral begins, and we can identify those density wakes due to the dynamical friction. And now both eccentricity and separation are decreased until the orbit stabilizes when the dynamical friction decreases due to the envelope dilution. And we can also see this nice ejecta shape. So this is another system with a solar mass red giant and 2 solar mass companion, again grazing its envelope at pericenter, but now ends with a core merger. And we see that all eccentricities still highly decrease during this spiral. And the amount of mass loss is larger for the larger initial eccentricity as earlier, even though it ended with a merger in this case. And now we tested some same first binaries of one solar mass red giant with 0.6 companion. But now instead of keeping the same initial pericenter, they all have the same epicenter on the edge of the envelope. And now the same images are initially located already inside the envelope. And we can see that even though if we calculate the energy and angular momentum for each of these systems, they get higher values for smaller eccentricities, since most of the ejection happens at pericenter and now they are located in a denser region, we still get the same behavior as with the system that we tested with same pericenter and different epicenters, where higher initial eccentricities led to larger final eccentricities and larger amount of mass loss, but now with smaller separation. And now we can see here the unbounded mass, which is also larger for the higher initial eccentricities opposite to the initial orbital energy and angular momenta. And this shows that the location of the pericenter has a great effect on the amount of mass loss and the corresponding eccentricity. Since all these systems have their entire orbit inside the envelope, small pericenters mean larger density, and thus the initial energy can be transferred to a larger amount of mass. Whereas if the initial eccentricity is small, it can only unbind the outer layers with higher velocities since they have lower escape velocities. And here is a system that ended with a merger, but now with same epicenter, which is now twice the size of the giant's radius. And we see that here all configuration also ended with a merger, but the amount of mass loss is correlated with the initial energy and angular momenta, and with opposite behavior to what we previously saw. Now the system with the smaller initial eccentricity ejected more mass since they had more energy and angular momenta and could transfer more of it until the companion has reached the core. And we still see that the mass ejection of the more eccentric system was faster initially because of this deep location of their pericenter. 2 minutes. Okay. So overall, what we find is that larger eccentricities at the onset of the common envelope increases the amount of mass loss, which happens mostly during pericenter passages. And the existence of the eccentricity at the end of the passing spiral can affect the delay time distribution for mergers of compact binary and then the resulting explosive transient. And we do see strong circularization and have quite similar values to observed post-common envelope binaries. And therefore, we can maybe suggest that since larger amount of mass ejection during the spiral may increase the final eccentricity, it means that most of the ejection of the remaining envelope will be through slow processes, as also suggested in a work that Andrei Goshev will present tomorrow. So now I'll leave some time for questions. So thank you very much for your attention.
Thank you, Hila. That was a great talk. I see Steve's hand up. I don't know if that's from last time or because it's, but anyway, if you have a question, Steve.
No, sorry, that was still left up.
Okay, do we have any questions for Hila? Yes, Jason.
Very nice talk, Hila. So I'm sort of very curious about this, the affecting the delay time distribution. And I don't remember, but I know for like PNE, there's been a couple papers maybe years ago that were showing two distinct populations of PNE forming with very different delay time distributions. So when you say can affect the delay time distribution, like how much does it elongate it? Just orbital times, a few orbital times, or hundreds of?
So I'm not sure that I can give you like a correct answer because it's only like a suggestion. We didn't really measure the eccentricity for the core merger because the core merger is also depending on the resolution, and we just stopped the simulation when we saw that a merger should happen. But if it is affect the eccentricity before the merger, so it probably can affect the delay time distribution. I cannot really tell you how much.
Thanks.
Any other questions? I have one question. So the starting on the apocenter at the surface of the star seems to, I mean, you know, there would have been previous orbits that would have changed the star already. So I'm wondering how far out do you need to start the true the initial pericenter of the orbit to have sort of a realistic initial condition?
Yeah, so you're right that it's not realistic, especially for the very high eccentricity case where the apocenter is just on the edge of the envelope. So we only wanted to measure like the effect of the location of this pericenter. And that's why we also simulated some other systems that their pericenter is not inside the envelope, but they also began with same epicenter. So this was just an extreme case, and you're right, it's probably not that physical and probably won't happen naturally.
One thing I'm kind of curious about is the tidal effects that Morgan was talking about. How would they affect the decay of the orbit so that common envelope could begin?
Well, yeah, so that's also something that we did not test here, but we'll leave it for others in their papers. But so we only test like a variety of different initial eccentricity and different mass ratios. But yeah, you're right that probably there will be more tidal effects before the onset of the common envelope that can also increase the radius of the giant. And yeah.
Hagai.
So actually, it's more of a comment. So actually wondering whether eccentricity can actually tell us something very interesting about, for example, aspects of recombination. If you have, and Hila mentioned this a bit, if the mass ejection happens fast, you actually don't have the time, potentially you don't have the time to actually circularize later on. So it would be very interesting to see models with recombination of high eccentricity initial orbits and see how much eccentricity is left in those cases where you have fast and mass ejection. Because if we are left with high eccentricity, that would be a very interesting way of distinguishing some aspect of this question. And in any case, we should expect initial eccentric cases, both as Hila mentioned from dynamical aspects, but Morgan did show that you actually do get there even after tidal interaction. So initial collisions should get there, maybe not as extreme highly, but 0.6, 0.7, I could certainly imagine these kinds of things happening.
Mm-hmm. Yes. Alexei.
Yeah, thank you for the wonderful talk. And I'm wondering mostly about what happened before the common envelope. So specifically, there were some discussions, for example, if you start with an eccentric binary, then the eccentricity could somehow make the onset of common envelope slower. So somehow the eccentricity first evolves, and then after that, maybe common envelope starts. I guess what I'm wondering about is were you able to set up binaries which do not enter common envelope whilst being eccentric? And the binaries, for example, which do enter common envelope, but do it not immediately, but after some number of orbits after exchanging mass and kind of growing the mass transfer rate?
So we did simulate some system that had a few orbits before entering the spiral in. So we do see this. Of course, it's more computational heavy. It's heavy, but we do see this. And I think there is also work by Sagiv Shiber that deals with avoiding the common envelope but still ejecting mass with eccentric binaries. But yeah, but we did not test it here. We did all of our systems ended with common envelope.
But the fact that you had systems which did a few orbits, then so that fact would probably then could make us say, or let us say, that the presence of eccentricity does not change the time scale of the onset of common envelope, I guess. So just leave the comment in there. I think it's an interesting conclusion.
Yeah.
Thank you.
Okay, any more questions? All right, thank you again, Hila. And I guess we have the last talk of the session, Sagiv Shavir. Sagiv, are you around?
You hear me?
Yes. Sorry. Yes, okay. So if you can share your screen, great. And I will give you a 2-minute warning.
Okay. Do you see my screen? Hello,
Yes.
everyone. My name is Giv Shiber. I'm currently a postdoc at Louisiana State University. I will discuss the unbinding of the envelope in grazing envelope evolution. I work on this project in collaboration with Roberto Iaconi, who was a postdoc at Kyoto University at the time. So grazing envelope evolution is an evolutionary stage in stellar binary systems. The onset of grazing envelope evolution is similar to that of the common envelope evolution. That is an unstable mass transfer due to, for example, the expansion of the more massive star while evolving to a giant phase. However, the key ingredient in the grazing envelope evolution is that an accretion disk forms around the companion, and that this accretion disk secretes the envelope mass at such a high rate that it launches jets. I'll show you a density map taken from one of the simulations as an illustration of this process. The jets are launched along the rotation axis of the accretion disk that is pinned perpendicular to the orbital plane. They remove mass from below and above the companion, preventing its complete engulfment. If the jets are not able to form or not efficient in removing mass, the companion will exhibit strong gravitational drag forces, which will pull it deeper into the envelope, and common envelope evolution will commence. Efficient jets, on the other hand, will diminish the gravitational drag forces, and the companion will stop spiraling in. If, in addition, a sufficient amount of mass has been accreted, in some cases, the separation will start increasing, and as a result, a binary system with intermediate separation would be formed. In a previous study, we performed three-dimensional common envelope simulation, which included jets. The purpose was to examine whether jets that are launched from the companion can bind a greater fraction of the envelope that was found in many other common envelope simulations, which did not include jets. The gravity of both of the companion as a point mass and the primary as a point mass plus the gravity of the envelope were included as well. We found that jets can bind 3 times more mass when simulated, and that the outflow is a bipolar shape. But this comes with the cost that the final orbital separation is larger. In this study that is the focus of my talk, we expanded the investigation by examining the effect of different companion masses. For this purpose, we simulated 4 different companion masses, 0.1, 0.3, 0.6, and 0.9 solar mass, and ran 2 sets of simulations, 4 with jets and 4 without. Other than the different companion mass, all simulations of the same set started with the same initial condition. We followed orbital evolution with each simulation, the amount of unbound mass achieved, the outflowing gas, and its geometry. We also looked for whether the interaction of the jets with the envelope results in a grazing envelope evolution instead of a common envelope evolution. In the remainder of the talk, I will focus on the simulation with 0.1 solar mass companion. So we initialized all our simulation by putting a 0.88 solar mass RGB star at the center of our grid. We imported the RGB star into the 3-dimensional grid from a 1D profile. The radius of the primary star is 83 solar radii, and the main sequence companion was initialized at twice this radius as a point mass. In the simulation with jets, we set the jet as we did in the previous study. We injected jets in 2 opposing cones centered around the companion along the axis that is perpendicular to the orbital plane. The 2 cones have a opening angle of 30 degrees and a length of 40.4 solar radii. The jet velocity is 400 kilometers per second, and the mass plate in which we inject the jet is 0.003 solar mass per year. These jet properties remain constant throughout the simulation time. And we used hands-on for our simulation and adaptive mesh refinement in dynamic code that was adapted to simulate common envelope interaction by also the Markov group. Here I show a 3-dimensional movie of density contours from the simulation of 0.1 solar mass companion. The white little circle is the main sequence companion that orbits the primary star, which is seen as a density contour, high density contour in red, low density contour in blue. The companion will start slowly spiraling towards the primary while constantly launching jets. We will see the jets coming out from the companion in blue. Started. In the beginning, the interaction is mainly due to tidal forces, and a bulge is formed in the primary envelope. At some point, the bulge emerges from the primary surface and starts railing the companion movement. Gravitational drag forces act to shrink the orbit, and the companion starts spiraling into the envelope. When the companion encounters the envelope, the jets unbind the envelope layers with which they interact. More and more envelope mass is removed as the companion spirals in deeper into the inner, more dense envelope. The envelope is outflowing in all directions with a growing outflow rate. As the orbit stabilizes, the jets have no more gas to interact with, and the outflow weakens, but does not stop. The result is a closed orbit, which is somewhat eccentric. How much mass do the jets unbind? For the 0.1 solar mass companion, 65% of the envelope mass becomes unbound by the end of the simulation. For higher companion masses, a smaller fraction of the envelope is unbound. This is in part because we kept the same jet power in all of the simulations, while the systems with heavier companions are more gravitational bound. When we simulated equivalent systems without jets, the amount of unbound mass was about 8% more. The companion in the simulation without jets spirals into a small separation without unbinding much of the envelope. This is a common envelope evolution. On the other end, the jets that are launched by the light companion of 0.1 solar mass successfully unbind the mass outside the companion's orbit almost throughout the entire evolution. This is a grazing envelope evolution. The unbinding of the envelope for this case continues on a longer timescale of 600 days. And at the end of the simulation, the unbinding of the envelope still continues, although at a decreasing rate. Here I show the final state of the simulation with a companion mass of 0.1 solar mass. On the left side, I present density slices of the simulation that include jets. On the right side, I present the simulation that did not include jets. There is a notable difference between the outcomes of the two simulations. On the upper panel, space on view, we see that the jets prevented the enlargement of the companion by high density gas. Edge on, we see that the jets remove the envelope from below and above the companion. Here I show density profiles on a straight line starting from the primary core, going through the companion and continuing outside the companion at 5 subsequent times. In all of them, there is a steep drop in density at the companion location. This indicates on a grazing orbit in which the primary radius can be seen shrinking simultaneously with the separation. In all of the other simulations, the density does not show this drop in density. In addition, the jets affect the geometry of the outflow. Without jets, the outflow is concentrated around the orbital plane with only a negligible amount of mass outflowing through the poles. This is expected by theory and also has been seen in previous simulations. The average outflow speed is about the escape velocity of the primary star. The simulation with jets yields faster outflow towards the poles, significantly faster than the outflow towards the orbital plane, with velocity corresponding to the escape velocity of the main sequence companion. Additionally, for lower mass companions, the mass outflowing towards the pole is as massive as the equatorial outflow. So for these systems, the jets produce a bipolar shaped outflow, which aligns with observation of bipolar planetary nebulae, where the rotation axis of the final system at the center of bipolar nebula was found to coincide with the axis of the nebula itself. To conclude, we investigated the grazing envelope evolution, where a main sequence star companion accretes mass from an evolved red giant bulk star and a large jets that interact with the envelope. We simulated several different companion masses, finding efficient unbinding of the envelope by jets in lower mass companions. The simulation of the 0.1 solar mass companion is the first to demonstrate a grazing envelope evolution in its entirety by reproducing theoretical models in three-dimensional hydrodynamic simulations, which strengthen the feasibility of the grazing envelope evolution. The jets produce bipolar outflow, which later can yield a bipolar nebula. Thank you for listening.
Thank you, Sagi. Howard Bond writes, congratulations to Sagi for giving a great talk 2 days after the major hurricane in Louisiana. I hope you and yours are doing okay after Ida went through a lot of damage there.
Yeah, I'm okay, although that I'm now working remotely from other states, so I'm not currently in Louisiana.
I see.
But
okay.
I have electricity and I have some friends there, and you're all right.
That's good.
Thanks.
That's good. Okay, we have questions for Sagiv. Yes, Jesus.
Hello. It was a nice talk. Can you comment on the jet's properties? For example, you said it was 400 kilometers per second and the mass loss was extremely high. Can you comment why did you choose those parameters? And if you run some simulations with different parameters to see how much mass gets unbound?
Yeah, so the jet velocity is about the escape velocity for a main sequence star. So, for example, for the star is about 600 kilometers per second. So we take rather conservative value of 400 kilometers per second. And also, if you change the mass of the star, it will also proportionally will change the radius, so the escape velocity will remain about the same.
But for example, we don't see very high like jet velocities in Planetary Nebula, for example.
I mean, in I think that so in observation you will it's like when you after the interaction the velocity that is flowing outside will be smaller than what we inject the velocities because we inject it around the companion. And also I think when vehicle sees some velocity jets around main sequence companion in post AGB intermediate binaries. And I think if you see this velocity as well. So I don't think it's too high velocity.
Well, I think it is observationally we don't see those high jets. And in one of your last slides, you compare with the velocity of the nebula. You have velocities as high as 300. Like, did you ever compare to any observations of the expanding nebulae?
Well, it's also to actually compare, but because we have a certain domain way that we need to assume something about to happen after that. But the velocities that we found to achieve at the boundary of the grid is about 100 kilometers per second at the pole. Around the equatorial, it's smaller.
Hans von Winkel says, so we do see these velocities on the jets. Do you want to comment further? Okay. But they're created in, okay. Created in
Thanks.
Go ahead. Okay, so he says they're creating an accretion disk around the companion. So we'll hear lots more about that on Friday. Any more questions for Sagi? So Luke has a question. Nice work on an interesting topic. Does your jet model accrete or remove mass from the envelope? If so, then how much? And how do you think the results might depend on this?
So we don't actually simulate the accretion itself because it's on a smaller scale. But we do not change the mass of the companion as a result of the accretion. But it's an interesting topic, and you will hear from Diego about new local simulation that we took the inner part around the companion to see how much it's accreted in the local simulation. Beside that, we assuming an accretion rate that is the Bondi or Littleton accretion rate on the surface of the star. So maybe I can show this slide. Okay, no. Yeah. So because the jet max per site and injected jet is constant, while the Bondi or Littleton accretion rate depends on the mass of the secondary, I get this ratio that is different for the companion mass. This is the third row in this slide. So, but we assumed a certain accretion rate based on the calculation of the Mondial accretion rate on the surface.
Okay, thank you. Any other questions? Okay, so we'll see more on Friday about jets. Thank you very much, Sagi. And now I guess we open up to general discussion since we have some time left. Everybody's worn out. So your simulations I missed, were they including MHD or hydrodynamic?
Only hydrodynamic.
Okay, so from what we were seeing in Fritz's talk earlier that even relatively weak magnetic field strengths could produce a strong bipolar outflow. I wonder, would that require you, for example, to change your jet model?
That's an interesting question. So we are talking about jets that are happening during the spiral, and we found in most of the simulation that during the spiral, the magnetic fields are maybe not that important. So maybe there is a two different roles or two different phases of jets. There is this during the spiral, which could cause a grazing level of evolution, and maybe later when the spiral is already ended, there is this building out of magnetic field that can inject more collimated winds and jets.
Mm-hmm. Hans.
Yeah, do you hear me?
Just barely.
Barely.
No, I can't hear you at all.
No, I didn't. So, can you hear it better?
Just very slightly. I don't know. Sagib, can you hear him?
Just slightly.
No, sorry. We could see you, but couldn't hear you. Okay, I think his mic isn't working or something. Okay, he'll type it. I should say we can have questions for any of the speakers in the session who are still on. Okay, so Hans says, those who did the CE modeling were there systems that did not spiral in, but left on quite wide orbits. Were left, I guess. Yeah, anyone? Morgan.
I don't have an answer to this, but I wondered if other folks might want to speak up. So it seems hard to stop a spiral inward when there's still gas around. And around in that sense, I think means on a scale similar to the orbital separation. But I've been reading some, suggestions from a while ago, and then more recent work thinking about like what happens when perhaps the donor star starts to contract dynamically due to the amount of mass that it's lost. So I don't know, I wondered, I don't know if Alejandro Viña Gomez is still on this call, but maybe we could talk about things like that. So one way to stop things might be if gas started to disappear on those scales.
Yeah. So Alejandro?
Can you repeat the last part, Morgan, please?
Yeah, so I just wondered if, like, sometimes we talk about like the contraction of objects that have lost a bunch of mass. Maybe that's a reason for halting an orbital in spiral. Does that ever happen at relatively large scales, or is that something that happens only at very small scales?
Do you mean like mass via previous stellar winds, or like some of the earlier options from the Roche-Loeb overflow interaction? I guess what I'm thinking of, and maybe we can discuss if this is the right picture, is that the point is the question that was made was about, can you begin kind of like a common envelope phase and then kind of exit it without do not go full into.
Yeah.
And yeah, so I guess some of the things that, yeah, so I always think of it in a very simple way, that a common envelope should be a result of this dynamically unstable mass transfer. So if you manage to get to a stage where you actually will form a common envelope, you should get past the first stage of the loss of co-rotation at least. And I think going back from that could happen in maybe some extremist scenarios where maybe you have some extreme nuclear burning or some sort of like transient that it's ignited. I'm thinking of what Podsetlovsky at some point discussed in the context of this nuclear common envelope. But this all seems to me, and I see that people have hands on, so I'll just finish with this, that is kind of like an outcome of a common envelope phase that leads to either a transient that will eventually lead to a merger or some sort of tighter orbit, rather than emigration outside of the common envelope phase space.
Okay. I guess, and the reason I asked you in particular was I was thinking about your paper recently about like stellar response after stripping.
Okay, yeah, but I think then that for
maybe
me,
maybe I was missing something.
No, I think that for me would be like a different scenario. In that context, it's more about after a common envelope phase. What's well, in this work we try to see what is the response of a star after we emulate the common envelope phase. And I say emulate because we grab a MESA model and then we chop it, then we stabilize it, and then we keep evolving it. And part of what the results is that if you do not remove all of the mass, and by all of the mass I even mean that you can have fractions of solar masses within, like above the core, then you might have expansion of the strip star or recently stripped star. And this expansion, of course, can lead, now I think this is what Morgan was saying, to an additional mass transfer episode that can happen as shortly as years or hundreds of years, and in some scenarios, even thousands of years. So there is this additional phase that actually could, but I think that the thing is like, it could lead to different outcomes. One of them is an extra transient where you have this mass loss that even if it's not leading to a common envelope, it can, however, eject some mass that can, for example, power up the recently ejected material in the first stripping. And this is possible because now after a common envelope, you are in a tighter orbit, and therefore if you eject material via non-conservative mass transfer, it will have a higher orbital speed that you need to be higher than that to eject the envelope. So you might reach the previous material in a sort of like a CSM interaction way. But I think I've rambled for too long, so someone else might have a comment or opinion about that.
That's an interesting thought.
Yeah, so Morgan, okay, if I may kick in, because I had similar thoughts the other day, and I was digging out some plots that Hjelming and Webbing produced in Hjelming's PhD thesis some 40 years back or so from now. And they essentially looked exactly into this adiabatic response of a star. Yeah? So what Alejandro was describing is sort of the thermal equilibrium kind of response of a star, but not the adiabatic response. And in this adiabatic response, you can indeed see, I mean, the standard picture of this unstable mass transfer is that you get into this runaway situation because you remove mass from the star, right? It becomes larger, you remove more mass, it becomes larger, and so on and so forth. But sort of this step can actually be, I think, interrupted if this old models are sort of correct. And you can, I think, actually get into a situation where you sort of become initially dynamically unstable. But then once you have lifted off sort of the first part of the envelope, maybe then the star actual direction, the adiabatic response of that star is that it's rather than going to shrink. And so I can imagine that there is maybe room in this parameter space that such a thing can happen. And if I sort of look into these plots from this PhD thesis from quite some time, this kind of behavior is maybe possible if the star is not so developed yet and has not sort of climbed up the entire giant branches, maybe an AGB star. So if you do this a bit early on in the evolution, then maybe this actually can be possible. But details are still sort of pending, I guess. But yeah.
Stephen.
Yeah, it's really nice to hear the Webbing, Hjelming stuff mentioned. There's also an even more antique from Bath that goes back to some of the comments earlier, especially by Noam, about convection. If you include the convection and you start offloading mass, the system's going to expand until you wind up with a radiative envelope, in which case at that point it's going to contract. So it may partly be, I wonder if this is partly an artifact of maintaining a constant entropy or an adiabatic structure. If you go super adiabatic and you start any form of buoyant energy transport, then because you've got to maintain the temperature gradient, as you offload mass, the system expands. And this will happen until the system turns into a radiative envelope, which means the opacity drops. And this might show up if you use a more realistic equation state. Just a comment from the Stone Age.
No, I mean, it's also, the depth of the surface convective layer, right, matters for this.
Yeah.
And so,
it's actually both, because the surface convection layer is just the outer skin here, right? And that also is going to affect the angular momentum transfer and mixing. So again, I would urge people to think about doing sort of the microphysics of this by taking other people's box models, bootstrap off of somebody else's computer time, and see if any of those provide you with coefficients that you can put phenomenologically into the larger scale simulations. And I've been doing stuff on the mixing problem and convection in trigger TNRs. And what we're trying to do is take the three-dimensional and put it into one-dimensional coefficients that get beyond mixing length. I'm sure you could do the same thing here. It would be a good synergy in the community, I think.
Mm-hmm.
So, only comment.
Yeah. Any other comments? Questions?
Yeah, maybe I'll share something.
Okay.
I refer to the question by Morgan, if we can stop the, I don't see it here, just a minute. If we can stop the spiraling in. So this is a famous planetary nebula that you see. Can you see my screen? Okay, so this is from Wikipedia, which is NGC 2346. Try to remember it for the exam. So we see here bipolar planetary nebula with a binary, and there are several experts here on binary stars and how a bond can say something. The interesting thing about this planetary nebula, which always attracted me, that the orbital period is 16 days, which is quite a lot. The orbital separation is above 20 solar radii. So the common envelope did not go here all the way to 2, 3, 5 solar radii. It stayed where most simulations stopped, but this is a bipolar nebula, which I think was shaped by jets, not only equatorial outflow. So this is a case where actually we stopped the common envelope quite far away. I don't know if there is a binary with a longer orbital period. Maybe the expert here on binaries of planetary nebulae, and Dave Jones, who built a catalog, can say something. But this is an interesting case. So if you want to stop outside, think about this planetary nebula. Yeah, this is my comment. Maybe somebody else can.
Yeah, so it's certainly, maybe coming back to Hans's original question, it certainly seems to happen, whether or not I understand it or whether or not any of us understand it completely.
I mean, is this perhaps a case where, the binary itself is shaping the outflow that makes the planetary, and this is not a relic of a previous interaction?
So if I remember correctly now, I just put it into the chat, the simulation that Fritz showed earlier, I think that ends actually at a final orbital period of the order of 13 days. And in many of these simulations that we are running, we actually have the opposite problem, that the in-spiral stops sort of at relatively wide orbits still, and 16 days or 10 days or whatever, that sounds pretty sort of okay-ish from that point of view. And we have rather the opposite problem, that we can't get them sort of close enough. So the envelope is, in some words, too easy to eject, if you like.
Yeah, I think for me, something of 10 days orbital period sounds like a successful ejection. But I come from a more massive perspective. I don't know, this is quite different with planets. Probably it is.
But Noam, what did you say the orbital separation was?
Well, if it's 16 days, I don't remember the mass. Maybe Howard Bond remembered. It's 25 solar radii, where all the simulations stop and say we can not get inward. But this is not typical, I think, what you find in numerical simulation of common envelope, because I think the bipolar structure is by jets, not just by outflow in the equatorial plane that somehow collimated the fast wind. I don't think this is the case here.
Not just blocking in the equatorial plane.
No, I don't think so. I think there were jets here, and I don't remember the large scale. But in many cases, we see kind of nice thing that maybe it's equatorial dense material, collimated spherical fast wind. But then if you look on the big nebula on the halo, you see really 2 points on opposite side, which are clearly jets. It's like young stellar object jets. So I think jets shaped it.
Any further comments, questions?
Well, as Fabian said, this is pretty much the parameters that we find in the simulation that I've shown, right? So it's 25 solar radii, orbital separation, and 12 days period there in the that's where our simulation stops. No matter whether we actually include magnetic fields or not. So this actually happens in both cases, in a case where we have a jet, in a case where we don't. But the jet is an extra feature then in the end that we find there. And that's unavoidable if we do the full thing with MHD included.
So you get the same mass ejection regardless.
Yeah, I mean, there's very little mass in the jet itself. Yes, this is low density material.
But the angular distribution is different. So, so is this something that could, like the planetaries that result from this, could you tell something about the magnetic field strength initially, or is that reaching some kind of saturation in the vicinity of the jet?
Well, the thing is that so the system that I've shown was actually one of the clearest cases that we had so far. I mean, there are others where the chimneys along which this collimates are not so clear, and where you actually get a more messy structure in the end. And the point is that you always get some material that is accelerating, has rather high velocities, but it's not always this clear jet. It's also sometimes a bit more lopsided. That also happens. Sometimes we have a jet on in one direction first and then in the other direction later. So there's quite a diversity of the morphologies that we get from this mechanism. Mm-hmm. And also, I think Norm actually said this in this lecture. I'm not sure. I mean, you actually referred to the precession that we may have or not have there. Actually, in a simulation that I've shown before, the jet is sort of bent, and it seems like a precession. Whether it really is a precession, I'm not so sure. It's not really a disk from which it comes and precesses, but it's sort of the foot point of the jet shifts slightly in the simulation because it's such a messy flow there, and so it's not really a straight jet that we have there.
No, it's a precession. You really see the two sides behave the same. It's not in your case. Like there's a famous, I don't know if Dave Jones is here, the famous paper with the binary and aligned. So precession, the two sides behave the same. So yes, the idea that at the end of the common envelope, you have a funnel that collimate outflow. Yeah, this isn't, yeah, it can, and I think it does happen in some cases, but in most cases of jets, I don't think these jets can explain precession or can explain the extra momentum that, Javier Alcolea and Bukharabal and all these people for 20 years now telling us we don't have enough momentum. So we need stronger jets from accretion. But this process of funnel probably happened in some cases.
So what do you mean by stronger momentum here? So what is the point here? I mean, the mass that you have in a jet is probably low. The velocities are pretty high, so they actually reach the velocities that are observed, right? It's 130 kilometers per second. So
yeah, but I don't remember the number. We need to work it out. But this picture that I brought you, it has a very nice shape that resemble your structure of the envelope. So the shape can collimate something, but I'm not sure. I'm not sure if the momentum is large. I remember that maybe I'll share the screen. This is from my paper from '92. I show quarter of the meridional plane. So you have more, of course, structure here, and it's continue here and here. So this is the equatorial plane. So here you have the funnels. But then I notice it doesn't give you the precession and some other problem that I listed there. So, but it does happen. But momentum, I don't remember the numbers.
The velocities that were quoted yesterday were exactly what we find. It was something like 50 to 130 kilometers per second.
No, this is fine, 50, but you need lots of mass because it's momentum, and many jets we see up to 300. I don't remember the numbers, so I don't want to say. I remember that didn't explain it.
Well, we've had a few more comments. I'm going to have to go actually because I need to teach. But Fritz, if you could maybe take over the discussion, we're going to continue.
Sure. If there's more comments or more things to discuss, I actually don't have much to suggest. The thing that I found interesting was sort of the discussion about convection and whether it plays a role here and what is needed to resolve this in 3D simulations. And so I thought a bit more about this, and well, now Paul is gone, but he actually sort of said, well, we cannot resolve convection here. And I'm not sure I agree with that, because in the end, it's not that we have to resolve the full turbulent cascade here. So it doesn't matter that we don't reach these high Reynolds numbers. The important thing for the transport is that we resolve the large convective eddies, and I think that is possible. And that is actually reproduced in the in some of the initial setups, but it's quickly destroyed, and therefore it doesn't really lead to too much of energy transport.
Yeah, Fritz, I'll just say something. I sort of agree with that too. I think there probably is some sensible stuff that can be done. Your point about resolving the full cascade, I think, is a good one. I don't necessarily know that you need to, so I would agree with you.
Yeah, but of course, I mean the situation. So Emily looked into situations with other light companions, right? And I think their convection may still go on undistorted. That's something to check, right? And it may be a matter of what the mass ratio really is in these systems.
So observation is what differences do we see for different mass ratios?
For different mass ratios? Okay. Well, the thing is that if the companion is very light, then it does not actually sort of lead to a strong dynamical response of the envelope, right? So it's just spirals in, and in the end it will merge with the core. And in this case, I think the structure of the envelope may stay rather undistorted. I'm not sure though. I mean, I still see the spiral shocks, and I don't actually think that convective motions can extend over a spiral shock structure. That's another problem for maintaining convection. It's sort of cut by these many spiral arms in there. So I don't know whether it will persist, but it's a possibility at least. What we see happen is actually in very late stages of the in-spiral, you have shear between these spiral arms, and that actually may in the end develop into a kind of large-scale convection, but that is not the convection that you have in the beginning in the star. That's a sort of due to the shear instabilities. And there, the thing is that you see that mostly in the simulations where the recombination energy is not taken into account and you don't expel the envelope. And then you actually sort of develop this large-scale convection. But if the envelope is lifted anyway, then this is actually also not persistent for very long.
But do we ever see the very short period post-common envelope binaries that we actually see in observations? Do we ever see them in simulations?
Well, that's a problem. We don't actually. And yeah, I mean, of course, the simulations, most of the simulations actually end at an arbitrary time, and you actually are in the slow in-spiral phase, but the orbital separation is still decreasing. Now, in the simulations that we run for very long, then there's not much envelope material left anymore, and then the orbital separation also does not change much anymore. But of course, and that's something that we're interested in checking, if you actually launch an outflow by a strong magnetic field or so, or if you actually sort of get this contact binary in the end, that may actually also change the orbiting.
But would tidal effects be important and much longer timescales?
Perhaps, yeah, but that's hard to tell from from simulations. The much longer time scales always difficult for us.
No, but once the envelope is ejected, you can follow kind of analytically the tidal evolution. You don't need to do the whole simulation at this point. So I just wondering whether they're close enough and large enough so the tides could still take them a bit and just the few more days in orbits. I mean, this is actually a simple question. Did anyone actually take the result of the simulation and then follow the binary long term, just using simple analytic methods?
But then you either have to take a system that completely ejected the envelope or assume that it was ejected, right?
Yeah.
Because if you have leftovers, then you cannot really.
Yeah, but if we take one of the cases where we use recombination energy, so we have 100% envelope ejection. So now we're fine. We know this is an upper, okay, it's the limit, but let's assume that actually really works. And you can do follow this next stage on long time scale.
What kind of evolution do you expect? I mean, you need to have some other, the companion accreted mass, now it's not thermally relaxed, it expand, lose mass or something like this. Amit Kashi did calculation where you have a circumbinary disk and look what happened, assuming tidal interaction between the binary and the circumbinary disk. Sometimes you get merger, sometimes not. So you need to assume something because you neglect it during the common envelope evolution, like accretion or whatever, sometimes eccentricity. And so the question is, how do you continue it with what tools and what you expect? But sometimes, in Planetary Nebula, you can have the central star can go through a late helium flash. In that stage, it inflates another envelope, and that can be an interaction that forms maybe to some of the planetary nebulae with very little mass, less than 0.1 solar masses, might come from a late helium flash that starts a common envelope again, actually. When it's separated, you have a late helium flash, which inflates a little bit helium that stayed with a little bit hydrogen, inflated, you have another common envelope. So I don't know who did the simulations, but people do discuss some of these processes. Yes, I finished.
So yeah, I think it's extremely sensitive to what you assume is the conditions around it. And again, to bring out this work that we just did, the thing is that within a solar mass coordinate in the context of double neutron star forming system, so again, high mass, but if you end up with more than solar mass in like just around your envelope, that not even taking into account any gaseous material or so, that would lead to an extra mass transfer episode. If you end up all the way to the core, then of course you would have probably something explosive or more like a merger-like sort of thing. And then you only have like a very tight place where even though like you might stall as a kind of like binary that will not do anything else. And then is this in that call it the Goldilocks zone post common envelope, or in this special place where you can, just have this and then maybe evolve without taking into account other interactions. Like you can use those simplifications to evolve forward, but I think it's very sensitive to what one assumes. One can make a few cases and then model them forward, yes, but I haven't thought about it, and it sounds initially complicated.
Fritz, maybe you can close this session. We are over time, unless somebody has something to say, but we are decaying in the number of.
Yeah, I noticed. I just was looking into what Javier just posted into the chat about the momentum problem.
Okay.
And so he said that this was actually a problem associated with driving planetary nebulae with photon pressure and dust rates. So that was a specific problem. And there's also a link in here. So if you're interested in that problem, maybe look into the chat, because that will be gone once we close the Zoom session here.
Well, it's a classical paper by this group, wonderful series of paper on the momentum. Yes, it's a different situation of post-AGB, but they don't have the post-common envelope, this post-AGB, so they need accretion around the companion. Okay.
Yeah. All right. Just wanted to point out the chat here before it's gone. And then I would like to close the session. Thank you very much for participating. Thanks for the interesting and stimulating discussions. And yeah, see you tomorrow.
Thank you.
Do you want to close the session for today, or?